All right, so on 29, lefts are under because it's always increasing. On 30, midpoints, we don't know because we don't know the concavity. So it might be true. 31. Must be true. Lefts are going to be under, rights are going to be over, so lefts are definitely less. 32. Must be true. Now, lefts we know are going to be under. Midpoint we don't know. Midpoints could also be under, but lefts are going to be worse. Lefts are going to be farther under. So if you have a graph, if you have a graph that's concave up, a midpoint rectangle, remember what a midpoint rectangle is. It's that pivoted trapezoid, right? That would be a midpoint rectangle right there, a pivoted trapezoid. Well, a left is going to be, there. I mean, so a left is definitely going to be less than that pivoted trapezoid. So they both might be under, but left is going to be more under. And so that must be true. What about 33? 33. Must. Same reason. Trapezoid could be under if it's concave down. If it's concave down like this, a trapezoid is going to be under. Okay? Trapezoid will be under. But what would the left look like? A left would look like that. A left is going to be more under. And for sure on a concave up, a trapezoid's an over approximation. So trapezoid's going to be less, lefts are going to be less than trapezoids. So it must be true. 34. May be true. We don't know. Trapezoid midpoint depends on concavity, so we don't know which one is under, which one is over. So that may be true. Okay, so you'll get a chance to do some more like that. Ask about those. Okay, let's talk about 51. This divide and conquer. Now, I probably should have had this one on today's homework, or for tomorrow actually, because we didn't really talk about it, although all you had to do was go back in the section and read about it a little bit, but we don't do that very often, and so you may not have thought to do that. Divide and conquer. Here's what it means. Now, on this one, the integral goes from 0 to 2 of sine of x squared. And they're asking us about, is it lefts and rights, or is it midpoint and trapezoid? Midpoint and trapezoids. And they're talking about trapping the integral. Here's what that means. Okay, so this is I, the exact integral. Okay, and so they want us to trap it using midpoints and trapezoids. What that means is find a number that we know is less than the integral, and find a number we know is more than the integral. So we should look at the integral to see if trapezoids are going to be over or if trapezoids are going to be under. So Callan, let's redo this one. Let's graph that one from 0 to 2 this time. So change your window, and let's do a zoom fit. Let's go 0 to 2. Now, as soon as he gets this up here, so now, as he's doing that, are trapezoids or midpoints, what's going to be under? What's going to be over? Depends on concavity. Does the concavity change here? It does. That's what the divide part means. The divide and conquer strategy means let's divide this into its parts that are concave up, concave down. How would we do that? Now, you don't have to do it. You just have to explain how you do it. Inflection point. So if we actually had to do it, we could do the second derivative, set it equal to 0, right? We could find those inflection points. So let's just guess. Let's say one is about here. That looks about right. Changes from, let's say right here, this changes from concave up to concave down, somewhere in this vicinity. Okay, that's at about 0.7 maybe. Okay, and then maybe over here, I don't know, right in here somewhere, maybe at about 1.9, it looks like it might switch concavity again. Concave up, concave down, and then concave up again. So over here, when it's concave up, what would be under? Midpoint would be under, right? So we could maybe do 10 midpoints, let's say, in here, and we know that would be under. And what would be over? Trapezoid. And in here, what would be under? Trapezoids would be under. So maybe we could do 10 trapezoids in there. And then here, it'd be the reverse again, back to midpoint. Okay? So what we could say then is what would be under would be 10 midpoints in the interval from 0 to 0.7. And 10 trapezoids in the interval from 0.7 to 1.9. And 10 more midpoints, I just picked 10 out of the air, it doesn't really matter. 10 more midpoints from 1.9 to 2. Does that make sense? So this would give us an under approximation, this would give us an under approximation, and this would give us an under approximation, but we divided it up into those intervals so we knew something that would be under. And then over here would be the reverse of that. We do 10 trapezoids, 10 midpoints, and 10 more trapezoids over here, and that would give us a number that we know would be more than the actual area. And over here we'd have a number that's less than the actual area, and we trap the integral. Because this is an integral we don't know the exact answer of, this would be a way to trap it and know that we've got to have it in there. Now we're doing a lot of theory kind of talking here. I want you to understand the thought process. Now how much of this you're going to actually have to do on our next test? Not that much, okay? But I really want us just to be thinking about, okay, we've got this dilemma, we've got this integral, we can't do geometry, can't do the antiderivative, all we can do are approximation techniques. How in the world did some smart person, who probably at one time in high school was sitting in a calculus class just like you, very smart people, and then wrote these programs for the Texas Instrument Calculator so it would do this integral, right? And get lots of money by us math teachers who pay them for these calculators, okay? But that's what we want to try to understand. That's what we want to try to understand is how they do it. So we're just talking about how, okay, we don't know what this is, but are there some ways we can narrow it down a little bit? And that's kind of what we're saying, okay? So we can narrow it down and doing that. Now we're going to actually do one. We're going to do some calculations, and we're going to use that little program, that calculator program that I gave you. The rule's going to be if we do 10 or more subdivisions, you get to use that little program, which I'm going to show you here in a bit. If it's less than that, we're going to write them out by hand. But if it's more, we'll go ahead and just let that program calculate. Because we're mostly interested in just the idea of what's happening. Okay, so that's how we can do it. That's what 51 is about. Okay, so let's go. Is that it then? Any other questions? All right. Let's move on then with a little bit of notation maybe. Well, I tell you what. Let's just do this problem right here. Let's do in your homework there in your notes, whatever. Let's go ahead and let's do that very same thing. We're going to actually work it out, except we're going to do it with lefts and rights instead of midpoints and trapezoids. So we want to do the same thing. We want to take this integral and we want to trap it using left and right rectangles. So we'll go back to Callan's picture here, and what would be, using left and rights, what would we be interested in? Increasing, decreasing. So we'd be interested in this. So we're going to cheat a little bit, and we're normally to find a maximum, we do what? Awesome. Derivative, set it equal to 0, right? Find the maximum, but let's cheat. Okay? You guys have made it the 4th term. Congratulations. We're going to let you, take it easy on you now.
Congratulations yet.
Oh, yeah, you can still drop today. Okay, you're right.
Tomorrow.
All right. Yes, it's going to be a very difficult 4th term. Very difficult. All right. So we're going to find this maximum. There you go. Okay? Looks good. 1.25331 is where that maximum is. Okay? All right, so we'll go out to 3 decimal places. And, well, actually, one of the lessons today is that we want our final answer to be accurate to 3 decimal places. So you usually want to use more than that when you're in the middle of the problem. So 5 would probably be good here. So we're going to do that. So back to this. So it's increasing until that point. So what would be under? Left. So we'll do 10. Let's do 20. 20 left rectangles up until that point. So that's going to be from 0 to 1.25331. Was that the number? I think that was it. And then after that, it would be rights that would be under. So we'll do 20 rights from 1.25331 to 2. And then over here, we'll reverse that. We'll do 20 rights for the first part, 0 to 1.25331. And then we'll add, I put 10, I meant 20. And we'll do 20 lefts in the part from 1.25331 to 2. All right, so we're going to use that thing I sent you now to do this. All right, so Callan will lead the way for us. So what we need to do is we need to go back to that area document so you can close out your scratch pad, okay, or go back to the home screen or whatever, and get back here into this area document. So whenever I say, whenever you have a homework problem that asks for L10 or R10 or anything that's 10 or more subdivisions, automatically you get to go to this, okay? If it's less than that, we write it out. But you get to go to this area document. So you pull up the area document. Now, for those of you that were in computer programming, computer math, that's basically what this is it's some programs. If we scroll, Callan, if you just hit Control right now, just scroll page to page. Keep going. Keep going. Now, for most of you, I would say for almost all of you, you want to be careful and not change the program or mess with it. Keep going. Keep going. Okay, right there on 1.9. So if you scroll down through there, this is the program. So any of you that are interested, you see some else's and some ifs and some if-s and things like that. So if you're interested in some of those things, that's where that's what's going on with this. Okay. All right. So let's go ahead and go back. Let's go back to page 1.2. Okay, there's two different options you have for using this, okay? Probably the easiest option and most self-explanatory option is to do this right here. Just go to page 1.2, and this is just a calculator page, is all it is. And they've already typed for you RAM. That stands for Riemann Approximation Method, okay? What's going to happen is when we hit enter on this, okay, so you just, and all you can do this yourself. If that one, matter of fact, delete that, Callan, just delete that. Okay? All right, just retype it. Type RAM. And watch what, so you're on this, in this document, you just type RAM, left parenthesis, and you need the empty parentheses, and that's all you're doing. And then when you hit enter here, you're telling it to execute that program. Notice how it went bold? That means, hey, this is something special. This is something that was defined as a program. So go ahead and hit enter. And everybody else can do it along with us if you want. And it comes up with this dialog box. It says, okay, you're going to get left, right, midpoint, Simpson's rule, the definite integral, all that. So you hit OK. And it's going to ask you how many decimals do you want. I'd say 6 would be good. Okay. Hit OK. Now it's going to ask you for your function. Now you may have already defined the function in F1. Now the problem is, the scratch pad is different than the document. So if you defined it in the scratch pad, it's not going to be the same. So I would say the safest bet is just type the function in here. So let's type sine of x squared, sine of x squared right in here. Okay? So we get sine of x squared and hit OK. And then the left bound is 0. And I'm surprised it was 2. Okay, must have known. Okay, so we got lucky. So 0, 2. And how many subintervals are we going to do? We're going to do 20. Okay? All right. And there is our left, 20 lefts, 20 rights, 20 midpoints, 20 trapezoids, Simpsons, and so forth. Okay? Now, for the exercise we're doing, though, there's something not right about this. For what I was just having, this trapping thing we're doing. Those numbers aren't going to be of use to me for this. Why? Yeah, because we divided it up, right? What we just found was the whole 0 to 2 thing. Okay? So you guys on these two rows over here, you guys run the program again, but go from 0 to 1.25331, and you guys run it from 1.25331 to 2. Run the program again, but run it in that interval. Did you do 6 decimals there, Cal? Let's do 6. Let's do. See the pressure when you get the pressure. Okay. Well, I see he's doing that. So somebody got the L20 for this first one. Okay. Yeah, let's go 6 places. And then this one, the right for this one. Now wait. You weren't. Yeah, that'd be you guys over there. 3 2s, 406. Okay, and then over here. All right, on this one. 58005. And then this one. All right, and then let's add those up. Okay. So you guys over here add the left one up. You guys over here add the right ones up. What do we got over here? Left siders. 7 what? And over here. Anybody? How much? 86. Is that it? Yeah. All right. So what we did is we just found out again. Are there? It seems kind of silly just from a usefulness standpoint. I know we could have just typed this in, got the answer, what's all this stuff. Again, kind of the theory part of it that we're talking about. But so what we've done is we've narrowed it down by using 20 of those and using the fact that we know when lefts are under, when rights are under, when lefts are over, when rights are over. And that idea, we found that, broke it up into pieces, and we did those parts. And then we also learned how to use this little program. So for many of you, you'll probably just use that, the RAM program. Now, I do want to show you this other one that's in there. So, Calvin, if you go back to the document, and if we scroll ahead to the next several pages, now keep going. This just kind of explains, this explains just some basic stuff about Riemann sums. Now, right there, it says RS parentheses B comma A comma N. That stands for Riemann sum. That's just a little sub-program or a little function, if you will, with those inputs that will just do it for you also. It will give you the left, right, midpoint, and trapezoid, and it'll actually give you exact answers, which is usually a pain. We'd rather have decimals, so you got to remember to get control in it. But if you hit RSA, go ahead and go to the next page. What was RSA? Oh, okay. I think that's just an approximation. I think that just gives you maybe the decimals. Maybe that's the one you should try. Just RSA. Gives the oh yeah, scroll down. There we go. That's what you want. Gives the approximation for the above. Yeah, so that's the one we want to use. That'll give us decimals. Okay, and then go to the next page. If you only wanted the left, you could do RSL. If you only want the midpoint, you could do RSM. If you only want the right, you could do RSR. And Simpson's rule is that. Okay, so now go to the next page. And so on the next page, they give you just a blank calculator page. Now it says RAM. Go ahead and delete that. And let's do, let's just type RSA. Oh, wait, delete that. Sorry. We need, for this, we have to define our function ahead of time. So this is not, the first program is kind of hold your hand, right? I mean, the menu comes up, it makes you enter everything you need, how many decimals. It's kind of nice. I mean, I like it. This is a little more rough, okay? This is more where you have to do more of the dirty work. Okay, those of you that were in programming know that a good program takes a lot of the work out of it. The user just gets to just answer the questions and type it. That's good. Okay, here you're a little more on the inside of things. So here you'd have to type define. So let's do that. So we type define. space, and then f1 of x, and it uses, inside the program, it uses f1, so f1 parentheses x equals sine of x squared, and hit enter. And then we would type RSA, and it'll go bold, meaning that it recognizes that as a program, parentheses, and then it was b comma a comma n. So we would go 2 comma 0 comma 20 if we were wanting to do 20. And that would be a Riemann sum approximation, and go ahead and hit enter. And there it gives you all of them, and it goes out to like 12 decimal places or something like that. Now type RSL, parentheses, 2 comma 0 comma 20. And I don't know why I did b minus a, that's just the way they wrote it. And hit enter. And it gives you just the left. Just the left. So those are other options. Now, you don't have to go to 1.7 to use those. Let's scroll back. Scroll back to 1.2. Just on any calculator page in this document, you have to be in the area document. Okay? So if you go back to page 1.2, if you typed RSA right now, it would recognize. See? It would recognize. So you could do any of these. So you could type the RAM with the empty parentheses, or you can type these other ones, and do them that way. Like I say, RAM is probably the most user-friendly. So whenever I say use your calculator, use the area document to do these, this is what I'm talking about. You open up the area document, you go to page 1.2, if you're going to do RAM, you type RAM, empty parentheses, hit enter, and enter your information. Okay? So that'll be the expectation probably on the next quiz that you can do that you can get into that document and you can use those things. When it asks you to save it, you don't have to save the area program. It'll just save that work you've done and stuff. So when you get out of it, it's up to you whether you save it or not. Okay. Let's talk about a couple of things here, and then we can get basically into our homework. So we've got that document. Let's talk about this notation again. So something you might want to put into your notes. We're going to be running into this notation quite a bit here in the next few days and into early part of next week. Is anybody going to be gone tomorrow? Okay. All right. Yesterday we said that this side, this was what right here? What did this represent? Error, the amount of error. This is the amount of error that a left rectangle has, however many left rectangles, okay? Because this is the exact area, and this is the approximation that the left rectangles give, and the difference would be the amount of error. So this is the amount of error. And then this less than or equal to something. What would be a name for this something? If the amount of error is less than or equal to, let's say that's 0.1 or something. Let's just put something in there so we got something there. What would you call that 0.1? What would be something, a name we could give it? I like that. The max error. Now another term that they use is, this entire expression they call an error bound. An error bound. Now remember, when you take off the bars on a absolute value problem, it's like this. It would be like this. It would be an and situation. We talked about some of these at the very beginning of the year. If you take off the bars, it would become this. And it would say the amount of error is somewhere between negative 0.1 and positive 0.1. And that would all depend on what? The negative and the positive. If it's over or under, it just depends if the lefts are over approximation or under approximation. Okay? So that's all that means. It's an error bound. It tracks the error, if you will. Right? But it's the max error. That's the most it can be, because it says the amount of error is less than or equal to 0.1. Okay? It's kind of like a tolerance in industry, in manufacturing, right? This would be like, this would be the actual thing we're making. This would be the ideal, or what it's supposed to be. And maybe these are millimeters. And this would say, okay, the amount of error has to be less than or equal to 0.1. Maybe the radius of the bolt we're making has to be within 0.1 millimeters to be acceptable, right? That would be like the tolerance, the max error, okay? So that's what we're talking about on this. Now you got to think about this a little differently when you talk about max air, because there is no one right answer when you talk about max air. Okay, or air bound. For example, I could give you a bound, a maximum on the amount of money in my billfold. The max of the amount of money in my billfold is $1 million. Okay, and I promise you that's a true statement. Okay. Now, it's also a true statement that the max, the bound on the amount of money in my billfold is $500. Now, which one of those tells you more about how much money is in my billfold? The 500. It narrows it down more, right? But they're both true. They're both true statements. So this number doesn't say how much air is. You're not guaranteed that it's that amount of air or whatever, but you know for sure it's not more than that. So for sure I don't have more than $500. So the smaller we can make the max air, the more useful it is, right? The more useful it is. That's what I was talking, that's what we're going to get into when we talk about the calculator. How does it know it's within 12 decimal places? Well, what it knows from the formula, which we'll learn later, what it knows is it's within 12, it's for sure got 12 decimal places right. It probably has more, but for sure it's got 12 decimal places right, because it's working on a worst case scenario kind of basis. Okay, so there's going to be some problems in your homework there. We're going to get into that. I'm guessing you're going to have some questions about it. We'll see, and we'll get into that discussion once you get to that point. So I'm going to leave you, I think maybe I'll just leave you with that thought right now. And I did want to hand back those quizzes from, well, I meant to do that yesterday. And since I forgot to do that yesterday, let's do that now. And then we'll start working on it. Neil. This one. Miranda. Randy, Robbie, Brenna, Keaton.
You don't Look at that. Look at that.
Happy right. You'll be happy when you lose.
I made one, we read this story together, and then divide by 60, and I knew this as soon as I turned it. Are you proud of me, Mr.?
This was last term.
Okay.
Yeah, this one.
I have 100 calculus.
Yeah, a lot of 100%. A pluses so far. Yeah, I took points on that one packet. So now this one, at one point, I think these problems, I've got several different quizzes and different things I recycle, and we don't always do the same section. So, but anyway, this key is an older one where I had them do it without a calculator. Well, and then as we got into it, I thought, well, that was kind of silly. Like number 2 wasn't a lot of fun, adding and multiplying all those things up. And then, and I also said to draw a sketch of x plus sine x, which is kind of hard to do without a calculator. So I just told him to just draw any old sketch, and so I thought, well, that's silly. We should just do that. So anyway, that's why you see like a lot of these for answers, because we were using a calculator. So anyway, 4.751, 6.490 was the answer there when you do the fundamental theorem. And so 5 total points because there was a lot of stuff going on there. Draw a sketch, had to estimate, had to do that. Okay, number 2, yeah, number 2 was a little bit mean, maybe, of me. The units, miles per hour and minutes, did not agree, so you needed to adjust for that. You can't go probably not going to go 696 miles in 10 minutes.
See, that didn't make any sense to me.
Yeah,
You should
so,
just give me
Just divide by 60. But it was 4 points, and that was one of them. So you do have to make sure you got units in there. So, yeah, that was number 3. There were still some people, even as much as I tried to warn you about, remember the old sigma messy integral? Not messy, tidy, whatever. There were still some people who had like 2/5 in here or various things in here. Now, it's been a while since we've done this, so it might be a little rusty here with this. But remember the 2/5 out front, that was your width, so that turned into the dx. The messy stuff in the function is where the x was, so the 2/5 I, that's where the x was at. So there's no 2/5 in there in the function, it's just x, because what you plug in is 0, then 2/5, 4/5, that's the 2/5 I or whatever that you have. And then the 0 to 8, the way you get that, remember, these are left rectangles because you got the 0 to 19. So the way the left rectangles work, you start on the left edge. The first thing you plug in for x is the left edge. So the first thing that got plugged in is a 0. Now, I think some people thought e to the 0 is 1, maybe, because some people were starting this at 1. I'm not sure where that came from. But the left edge, you put a 0 in for I, so you got e to the 0. So that's the first thing you plug in is 0. Then the next thing is 2/5, then 4/5, then 6/5. And you just keep going from 0 all the way to the last one. Where you put 19 in, you get 38/5. Well, that'd be 7 3/5. That's 2/5 away from 8, which is where the left edge should end up, or the last left rectangle should end up 1 width away from the right edge. So the right edge has to be 8. So it's got to go 0 to 8. And then you do your fundamental theorem. It says evaluate the integral, so you do your fundamental theorem, plug it in, and go. Although I did allow, it just said evaluate, didn't say use a fundamental theorem, so if you did just type it in your calculator, get that, that's okay too. Okay, so 3 points there. And then on the back, 4 points for this doing it the other direction. You had an integral, 0 to 2 pi divided up into 8 subdivisions, so that's pi fourths. So that's your width. And then, so do your x-axis, so you'd start at 0, then go to pi fourths, 2 pi fourths, 3 pi fourths, 4 pi fourths, so that's I pi fourths inside the sign, and then the sigma goes 1 to 8 because there's 8 subintegrals. And then these were the ones where we distribute this, you get I squared plus 2i, then you split it up, do your formulas that were at the top of the page, and it came out to be, what, 85, I believe. And then the last one, which is, well, I noticed there were some, we talk about calculator and don't use a calculator, don't need it. There were a few people that have a few addition issues or some multiplication issues. I think for sure at least once I saw 5 times 6 was 11 or something.
That's kind of funny.
Well, I mean, you got the calculator, but who wants to do it for a problem like that, right? You just do it in your head. I mean, so I get it, but so unfortunately that happened to a few people. Now this was interesting. I didn't think about this when I wrote this problem. I was thinking about, okay, I want to test them to make sure they know that on sigma notation you can't go backwards, so the sigma's got to go from 1 to 10, it can't go from 10 to 1. It's got to go from 1 to 10, so how are you going to make those numbers work? Well, you're going to have to subtract or something like that, so like 11 minus 1, 11 minus 2, 11 minus 3, 11 minus 4, I thought, that'll be tricky. And then I started seeing people with this. So you out-tricked me. So I looked at that, and there were a couple I marked wrong. I was like, no, that doesn't. And then I started thinking about, like, oh, wait a minute. I guess that is the same thing. It doesn't really. I mean, so since it is addition, you can do any order you want. So I had to count right. So anyway, so I out-tricked myself, I guess. How many people did that? How many people did? So that's good. Yeah, that was easy.
At first I was like, this is weird.
Why would he give us such an easy one? So anyway, so it was supposed to be more challenging than that, but evidently you guys outwitted it. So and then this one was 4 points, and these were the 4 parts I was looking for. Now, I want you to explain it obviously better than this, but I wanted you to mention that this represents the height or length of the rectangle. This represents the width of the rectangle. That's important. But when you're multiplying those to get area, And that, I think, is important. So I don't think it's enough to just say this represents rectangle areas. And why are they rectangle areas? It's because it's the height times the width. And then the sigma and the limit is adding up an infinite number of those. And that's how you get the true area under the curve. Okay, so that's what I was looking for there for those 4 points. All right, let's go ahead and pass those back in. And all right, the homework is the next line. Okay, the next line on the assignment sheet. And there's going to be a number of them in there that you'll use this area thing on your calculator. So if you guys aren't charged yet, you may need to share it with somebody. Okay, so the next line, and there's some more of those true, false, or might be true, must be true, can't be true kind of things. There's one of the trickier ones is number 5. I think it's a first problem, second problem. First problem? Yeah. So look that one over, talk it over with each other, look up the answer in the back even. And if you're not understanding what that is, let me know and we can discuss it.
With a great skill No. It's so cool.
That is awesome. She didn't do it.
Yes, I did.
Oh. Oh.
She literally said, by the way, this time ready. Yeah. I'm so glad. Like, I didn't feel like that. Yeah, she did. She told me second one. Oh, they were talking about it.
You may.
She sounds hideous.
So you did get the document? You
Class assignment?
class.
Okay. So everything up. See, where are you going?
Did you get the doc? Did everybody
I
get the
got it.
document?
I waited until I got it to put it
So you might not have it.
I think it turns your calculator off.
Okay. So let me. Okay, go ahead and log in. in. Okay, did you get it? Go ahead and open it. I would say no. Okay, now are you on this page that's on the screen there? Okay, now go to Doc, and then File, and then Save As. And then go scroll down to the My LIB folder. And choose that. And that's, you want to save it in there. Okay, so. Okay, then go, so to do it. Okay, so now go to the Doc button again, and then down to Refresh Libraries. Okay, all done? Okay, now go over to the 1.2 page, just scroll over one page. There you go, now hit enter. And then does the program run? Okay, you're good.
My sister just got 161 on
A what?
My sister just got 161.
I've never, she